record this because Zane asked. Alright, no problem. Alright, let me copy it over. Copy over 3. There we go. So space x capsule orbiting the Earth at out of 800 kilometers when expanding. What's the weight force? So the weight force, uh, I if it at 800 kilometers, it probably isn't going to change the answer if you use the gravitation equation, but I'll do that anyways. It's probably just going to be uh, 9.81 or really close to 9.81 times 70. But I have to look up the radius of the Earth and the mass of the Earth. -670 -11. 5.72 E24 times 70 divided by 3958. That's in miles. Let's not do that in miles. There we go. 6.37 times 10 to the sixth. Yeah. What I got is, answer I got is. Let me quickly type it out. It's 687.17 is the answer, and I'll quickly put that here. And then the way I, for 3A, and yeah, because how I got it was I just did the force of gravity equals G, and then M1 M2 over radius squared. And oh wait, hold on. I forgot to add 800. Hold on. 800 would be okay, I got 6.86.99. Huh. Uh mhm. I would just try to always change your units to be uh you'll basically always be using kilograms when you're plugging stuff in. Kilograms, yeah. Uh, uh, you'd want to just be using just meters for distances. That's it. Yeah. And the gravitational constant is that 6.67 times 10 to the negative 11th. Yeah. It's 5.972 times 10 to the 24th. Hmm. Why are you doing times 10 to the third? Uh, oh, oh, it is. Oh, hold on. Oh, that probably won't change it, but that may be why we got different. Hold on. 800 times 10 to the third, and then that's squared. Ah, I got okay. So now I got 542. I didn't catch that that was kilometers. Makes sense. I got 542.38. Is that what you got? That's times 10 to the third grams. That'd be in newtons, not uh. Yeah, it's in newtons because it's a weight force. Yeah, it would be. Uh, let's, hold on. Uh, yeah, so like so yeah, the unit for the gravitational constant is Newton uh newtons meters squared per kilograms squared. So it's the units are right now quick is newtons uh meters squared per kilogram squared. So in here, because you're multiplying by two masses, this would cancel, and you're dividing by a distance squared, this would cancel and be left with newtons. Hmm. Yeah. So and then that's why for the field strength equation, it's just one mass, but you use the same constant because then that's force per kilogram. And that's like your 9.81 because the 9.81 is gravitational field strength, and it's 9.81 newtons per kilogram. So that's just a constant acceleration downwards. So for the gravitational field strength, it's uh, G or not G equals F or it'd be field strength. So Fs G equals G m1 over r squared. So this would give you if you do the same thing, you have newtons meters squared over kilograms squared. Your meter squared would cancel and your square would cancel, so it'd be newtons per kilogram. And that's like, and those values that you'll get from this equation are like the 9.81 used for the acceleration for gravity. Yeah, it'd be the Earth. Yeah. For this, it'd be different because you're 800 kilometers up. But yeah, like that's how you like this is how you get that 9.81 value is with this equation. So if you're solving for gravitational field strength, or you're solving for an acceleration of something or a force on something, but you don't know the mass of it, you would solve for a field strength like this. And you can say that it's this is the acceleration it would be experiencing. The IB one, I can pull it up real quick. Uh, well, M1 can be. It doesn't have to be the mass of the Earth. Like if you're doing it on a different, it can be anything. But if you're doing like an orbital problem around the Earth, then yeah, it'd be mass of the Earth. And yeah, that's the equation you'd use for finding a force. If you're finding acceleration, you do the other one. And then, uh, so for the scale, I mean the scale would read zero because you can't. You're in free fall, so you can't like stand on the scale. If that makes sense. Yeah, because yeah, you look at them. 'Cause it's like I mean, imagine if someone in the International Space Station was trying to weigh themselves on a scale. Like you couldn't stand on it. It'd be the same thing here. Uh, for you talking about for A? Yeah, yeah. Yeah, I feel that. Yeah, IOC fun. Our IOC's got pushed back so far. I mean, I thought that was far because Uh, we did it in like the second month we came back to school, and then I've had assignments from Mr. Berger that have he has graded 3 months past when we turn them in. Uh, it's been fun. Yeah, yeah. Uh, mhm. I mean, tension is just it's either just gonna be a force, or if they're gonna try to do something to solve for tension force, it's just gonna be like it's gonna be like a spring. It's gonna be a really, really, really stiff spring, but it's gonna be like a spring. You probably won't see that, but if you do see it and you see that like and you see them giving a spring spring constant of a rope, then that's what they're doing. They're just treating it as a spring. Hmm. Hmm. Well, the thing is here, you're not given a force for A at least. You're not given a force. Hmm. No, no, yeah, you're on the right path. Yeah. So so yeah, that's his new maximum speed, and you see if this speed here is higher or less than that. If it's higher, he doesn't survive. If it's lower, then he does. Hmm. Yeah. So the thing is like with a problem like this, the important thing to do is to take out of this what you can, because this is really like three different problem. It's using three different concepts in one, because it's using from the beginning here you can see that you have a radius here. So this is that's not a highlighting. Uh, you can see that you have a radius. You know that's going to be circular motion. Uh, you have a period, so you know it's going to be circular motion. And then you have do not fall because they're pinned to the wall. So you're like, okay, well, there's friction happening here, and it says static friction right here. So there's friction. So you know that you're going to be solving friction in a with a circular motion problem. But the key thing to take away here is that your friction force is not it's not using the friction force as the centripetal force. It's using it as differently, using the normal force uh, as the centripetal force. So it's really like he probably won't give a problem exactly like this, because this one is so specific that you're probably not going to see anything like it again. But he could give something else where it's a circular motion problem, but there's a weird force that's being used as the centripetal force. If that makes sense. Yeah, because the whack thing here is that if they were doing the free body diagram, this is the normal force. Like this. Hmm? Oh, have I? Oh, I have not been projecting things. I've been drawing, but like I haven't been. I've been mostly just talking about it, but I've been recording it for Zaina because she isn't here and she wanted me to. Yeah. So there you go. I'm projecting now. So the normal force is like this, and then the friction force is like that, and it's so strange because you're never gonna see you're never normally gonna see a problem where the normal force is pointing straight sideways, and yeah, it's just like, and that's why for these kinds of problems where it's confusing, the best thing to do is to diagram it, because then you can see it helps you picture the scenario better in your head. If you can say, okay, these are the forces acting on it, and this is what I need to solve for. Is to be able to draw it, to be able to break it down and understand the interactions that are happening. Because if you can say, okay, these are the forces that must be on it, there's only one force you're pointing inwards, so you know that this has to be somehow related to the centripetal force. Because this is the only force pointing inwards. Yeah. Angular to period is, so if you I'm gonna assume that you're given angular velocity in radians because it just makes it a lot easier. Uh, if you remember, 2 pi radians is one full revolution. If I can spell, is one revolution. So if you want to solve for the period, you can just say, okay, well that's supposed to be the time it takes to get one revolution. So with the mental analysis, you know that uh, you for like a run, if you want, I was about just for frequency. Uh, for this, you know that your radians per second, if you want your seconds, you want to do your 2 pi over radians per second. So you want to do just like 2 pi over rad per second. Because then this will cancel, and you're left with seconds. Yeah, that's a year period. For frequency, it's like the inverse. It's you have radians per second, and then you divide that by your radians, which is just gonna be 2 pi because that's one full revolution, and then you get your per second, your per your 1/2 second for your frequency. No, frequency is in hertz. It's always in hertz. Hmm. The period, if the frequency is 2 hertz, then the period is 1/2 second. Yep. Yep. You just multiply by 2 pi. Uh, uh, two times. Uh, yeah, 2 pi. 2 times 2 pi because you have it's a period. Oh no, hold on. Brain, work with me. It would be your velocity would be 4 pi. So you'd want to do. Uh, I know it would be 4 because I thought of this in my head and then I can't retrace my steps. Because it's if the distance is 2 pi, you're covering 2 pi in half a second. So then at 1 full second would be 2 times uh your 2 pi. So it'd be it's easy to do with frequency because the frequency is the number of revolutions per second. So you can just say, okay, because at that point it'd just be frequency times 2 pi. It's easy to do like that. But so it'd be the inverse for a period. It'd be uh 1/2 times, or it'd be 2 pi over period. That was yeah. Yeah, that's right. That's fine. It has been a hot minute since I've done electric fields because that wasn't on the AP stuff. Electric fields is there. Electric fields. Okay. Yeah, electric fields is uh yeah. There's some similarities with gravity with the force equation, but mhm. Yeah, not epsilon. What is not epsilon? It's not epsilon. I think that's the permeability of free space. I think. Yeah, yeah. It's the permittivity. It's the permittivity of free space. That's a very good question. Let me see if I can figure out what that is because I do not remember. It's apparently it's Coulomb's law. So it's also written as hold on, what is K? What is this K? K is the Coulomb constant. Okay. Um equals 1 over 4 pi primitive or free space. Um. Yeah, no, they are just constants. That's wait. Eh? Well, I mean, there's your answer. They're both constants, so it's just like yeah, no. It's on your page, but there's literally no variables to put in. I mean, okay. Yeah. 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 Oh, that's not P, that's rho, I'm pretty sure. Uh I think rho is a constant. Let me check. No, it stands for something. Oh god. Oh, I don't remember what rho stands for. Uh, that's not Ohm's law. RA over L. RA. I mean, A is. Oh, I think this is a. Is this coils? I don't think so. No, there's no turns. Hold on. R. Oh, it's resistant. It's resistance times amperage over L, which I'm assuming is like length. Yeah, amperage is current. So it's resistance times current over L. Oh, that's it. Might be area. It's resistivity. It's resistivity. Okay. So resistance is so with electricity is very similar to like plumbing in the sense that you can imagine that uh, the current is the flow rate through the pipe. The uh, voltage is like the amount of pressure on the water in the pipe, and resistance is how tight the pipe is. So the with this, it's the rho is like it's the resist. It's a value of a material. Resistivity is like a property of a material, like like it's like its density and that kind of stuff. So what this is that it's saying another way to write it, which is a better way to write it for this, is resistance is equal to uh, the rho. I am not gonna be able to draw that rho. Uh, times length over area. So it's, and this is actually a lot easier to understand. This is saying that resistance increases with length and decreases with area. So like the wider something is, if you're imagining it as like a cylinder, the easier it is for electrons to pass through. The longer it is, the harder it is. The narrower it is, the easier it is. The narrower it is, the harder it is. Excuse me, and the shorter it is, the easier it is. Like like that's why you use thicker wire for more current because there's less resistance. Increasing the length increases resistance. There's some, but it's like it looks like it's mostly simple stuff. What sign there? Uh, that's. I want to say that that's n is number of turns. Is that right? Or is n something else that I'm not thinking of? I'm probably messing that up. Oh, is it drift velocity? Oh, okay. So it's like yeah. So it's like the actual speed of the electrons, if that makes sense. It's like yeah. I mean, the, besides just plugging the values that I don't remember the names of all the. Let me see if I can look at the names what all the variables actually are. N is a constant. Uh, I think, or that might be the number of. No, that's the number of free electrons per unit volume, which is to be something they would give you, or you could solve for. But it's the number of electrons in a certain volume that can move, basically. Uh, V is the actual drift velocity. Q is the charge, I think. Yeah, Q is specifically the charge of an electron, assuming which you should be doing these things in units of electrons. And then A is your cross sectional area, and then I is current. Yeah, like it's not like there's a lot of like in conceptual problems that would use that, except and if they are going to use it, it's going to be immediately obvious because it's going to be saying something about electrons per unit volume. You're like, oh, well, that has to be drift velocity. Or if it says drift velocity, like, oh, well, it's drift velocity, so I'm going to be using this. It's that kind of stuff. Um, for for uh, electric field. So do you remember how with gravitational field it was the acceleration based off of the it was acceleration because it was the actual units are newtons per kilogram, which cancels out to be acceleration. For the like if you're thinking of a gravitational field, that solving that gives you acceleration, which well it actually gives you newtons over kilograms, right? Because you have the let me see, I still have it here. Yeah, so you have F, you have your force of gravity here, and then you have your field strength here, which cancels out and gives you newtons per kilogram. For this, there's a lot of comparisons you can draw between electric fields because it'd be you'd be using charges instead of masses, but it would be newtons per charge. It would be the thing you get from the would be the field strength. So if you're given a charge, you can uh, like substitute it in here, and you'll get a force. If that makes sense. Does that make sense? Mm-hmm. That that's electric field strength. Yeah. That's just electric. So that's if it's F equals K Q1 Q2 over R squared, it's not one of them. That's not one of the variables there. It is the electric field strength, like how that's the gravitational field strength. Little g is. So if they say that the electric field strength here is at x distance away from the charge is x, and they're asking you to find like the charge of the electric charge you're talking about, you can plug it into basically this, but you replace the G with the K and the M1 with the charge, and then you solve for it. Like I can just rewrite it real quick because that would make it easier. It's F. That's an amazing F equals K Q1 over R squared. So like if you're given an electric field strength, it's this F. Well, because this is uh this is newtons per coulomb. This is what the units of this is because it's the same as uh your because the other one is like this one, the one you have in your reference sheet is a force and it cancels out and it's K equals or K times Q1 Q2 over R squared. And if you can't and through dimensional analysis, this cancels out to be newtons. And here you're multiplying by one charge instead of two. So like through dimensional analysis, you can see that okay, well we're missing a charge here, so then this must be equal to this divided by a charge, so that you can move between them. Does that make sense? Like, can you? Yeah, this is the force of an electric field. This is basically equal to this force over Q2. Is a good way to picture it. Like ignore this, but it's F over Q2. Yeah, like if yeah if you're given a charge, if you're given two charges and you know both the charges, and your R is changing, then you would be using this one if that's how he's doing it. But if he's giving you a field strength and he's saying this is the field strength of at this distance, then this is what you would use for that. Hmm. Yeah, yeah, it's fine. Sure, yeah, yeah. I can try to draw. Okay. So you're imagining a circuit which is like I'm gonna try using the thing. It's like this, and then you have your resistors placed throughout. Is that what you're imagining? So like, what's the difference here? Mm-hmm. Yeah. Oh, are you imagining that there's something wired in parallel instead of series here? Okay, yeah, if you want to share your screen, that's fine. Oh, yeah. Yeah, I can. Okay, yeah, okay, yeah. Oh God, that's weird. Uh, it's current, cause so the voltage is just in between back here, in between the negative and positive terminals. There's a 12-volt difference, if that makes sense. Like it will go from you go up 12 volts, yeah. So and the current it'll always be moving from positive to negative, even though technically it's moving from negative to positive, but it doesn't matter. It's just solved as if it's moving from positive to negative. You solve circuits as if it's moving from positive to negative, but in actuality it's the electrons that are moving and they have a negative charge. So in actuality it's moving from negative to positive, but you pretend that that doesn't exist when you're solving circuit laws. When you're solving circuit stuff. It's weird, but mm-hmm. Mm-hmm. Uh, if that's how it, if you're drawing I3 as going down, then yeah, then it would still be the same. Cause so like the current when you have these kind of splits and you have like these different segments, the current like when you have here where it separates, uh, like when it separates off into where you have your purple I3 drawn, uh, that section of wire that's now split will always the current from the it has to drop the same voltage across both of those as resistor 2. There has to be the same change in voltage, if that makes sense, because they're in parallel. So, but the amperage won't change. Like it's hard to describe, but like the amperage in something wired in parallel doesn't change in that thing wired in parallel. The amperage will be the same the whole way through. It only changes at a junction. Yeah, that loads. Yeah. Hmm. Yeah. Uh huh. Hmm, so it's been a while since I've done one of these with multiple cells. Well, if we think about this like conceptually, if you have two 9-volt batteries and they're in the same circuit, and you're solving it like this, then the right answer would be if you say that there's no voltage drop over the batteries, right? But that can't be right. So, uh, what I don't remember is, can you draw a loop including both batteries, or do you have to draw the loop only including one? Like, would you want to draw one that goes from first battery, like instead of drawing it going all the way around the outside, draw it going around the inside? If that makes sense. Hmm. So the thing is that you might be able to, but it's gonna be easier to do if you only have one voltage source. At least how I'm thinking of it. If that makes sense, because it's like if you have if you're working with two voltage sources, it just makes it more complex. If you're working with one, then you'll have to, and then you can just solve it as a simple circuit without, as if it doesn't have another voltage source, and then you can worry about that later. If you're, it's better to try to deal with as few voltage sources at once as you can. That's how I would think of it. Hmm. If you're doing the loop in the second, yeah. Hmm. Uh, oh, couldn't you do it? Uh, couldn't you do it starting with like starting at the battery? Like if that makes sense, like well, because if that's the positive side, then yeah, it would be flowing. It would be flowing from positive to negative. So like for this, you would solve um you would do uh like you would do negative I, if that makes sense. Like you would multiply by negative I because it's in the opposite direction. Hmm. Well, the thing is, if you're doing the loop like this, uh, oh, okay, so treat the direction that I3 is pointing uh, as just a sign. As if it's going the same direction, it's positive. If it's going the opposite direction, it's negative. Right? So for this loop, uh, you're because you don't have any or you're not working with any like junctions here, if that makes sense. Like you're just doing as it if it was one loop, your current will be the same the whole way through, right? So it's just when you eventually add them up, and you say um, your your I your I3 from this loop will be going the opposite direction as your as what you have it drawn. But it should like if does that make does that make sense? Like it's flowing the opposite direction that you have it drawn right now, but it would still come out okay. You would still be able to solve it. Hmm. Yeah, you would subtract the voltage. Uh, well, so for this loop, if you're doing yes, okay, I see now. Yeah, so you would either have you would subtract the voltage of the battery. Okay, it's been a bit because they removed circuits from AP as well. And I took AP 2 years ago, but I haven't been reviewing it because uh they took it out this year. Yeah. So the can you state your question again? Hmm. Uh, if you if you're doing the full outer loop, then that is how you would do it. But like, well, because that's like I wouldn't do the full outer loop because it's easier if you think of it with just one cell. Because the thing is with the changing voltages here, the voltage from negative to positive for both of those should be 9 volts, but like that doesn't work because you'd have 18 volts on one side and on one side of the uh, cells and 0 volts on the other. Does it make sense? Wait, hold on. Yeah, yeah. I mean, from when I solved them, I tried to do them all with just with one cell. Is how I remember doing it. Because I remember being told by Mr. Mills that I mean, yeah, you can do it the other way, but it's easier if you don't because it's yeah. Yeah, I mean, you seem to understand it pretty well. Yeah, no problem. Yeah, 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 no problem. All right, all right, no problem. See ya. All right.